exponentials and logs. Today we integrate exponentials and logs, and they're logically related. So let's start just by review. Yesterday when we took the derivative of y equals a to the x, how did you do it? Natural log of both sides, so that we could bring stuff down, and then without doing all the rest, then we used implicit differentiation, yeah? What was the derivative of the exponential? Derivative of a to the x is? A to the exponential log of a. One person remembered it. That's not great. A to the exponential log of a. Cool. Come back to this. Let's build upon that right below here. So if we are going to integrate 2 to the x, wouldn't it be awesome if we had a natural log of 2 here, so the derivative was complete? Can I just throw it there without any regards to math rules? No. What must I do? Yeah, do both sides, which I don't want to do both sides. Instead, let's balance with, instead of multiplying by 2, we'll balance it with divide by 1 over natural log of 2 is what I meant to say, not just 2. So, now this is complete. It's 1 over natural log of 2 times, what's that, the antiderivative? What's the antiderivative of that? 2 to the x. So, when we take the derivative of 2 to the x, that's 2 to the x times log of 2. When we take the antiderivative of 2 to the x, it's 2 to the x divided by log of 2. Generally speaking then, the antiderivative of a to the x is a to the x over natural log of a. All right. So that's one of the big ideas of the day. Second, let's go back here. How did you start tackling this before you took the derivative? What did you do? You exponentiated, then natural log, and that brought down, and so y is natural log of x over natural log of a. Then we differentiate it, right? Pause there though, because that's good enough. That's the change of base formula. I can change natural log of a to natural log of x over not natural log of a, log of a with natural log x over natural log a to change the base. Now keep that in mind as we do this guy. If I want to integrate log base a today, we're going to change the base. It'll change to natural log of x over natural log of a. Natural log of a is constant, or numerical. So 1 over natural log of a out front, and let's just integrate natural log. That's just 1 over x, right? No, that's crazy. The derivative of log is 1 over x. The antiderivative is not. How do you anti-differentiate natural log? Ultraviolet voodoo. Okay? So what is your u? Natural log of x. What's dv? dx. And du is 1 over x dx, and v is x. So that this becomes 1 over natural log of a times the quantity uv, so that's x natural log of x, minus the antiderivative of voodoo. Voodoo is x times 1 over x dx. When I divide out the x's, I'm integrating just a plain old 1. What do I get when I integrate 1? X. So the antiderivative is 1 over natural log of a out front of x natural log of x minus x plus c. And so generally speaking, that is exactly what you get here. Now I want you to see where it comes from, but if you get this in the homework and you remember it, great. If you don't remember it, I guess you got to do this. But you don't have to do the development every time unless the question specifically says, show where the work comes from or something like that. You with me? All right, now those are the two big ideas. That's technique. Let's talk applying it within. So you could then apply that or use it in conjunction with other integration ideas, like the first one. That's a product. One's not the derivative of the other. What kind of technique would you use? How do you tackle a product where one's not the derivative of the other? It's not a chain rule derivative. Ultraviolet blue. So what should we let u equal? X, and therefore dv is half to the x dx. Okay? Du is dx. All right, well, here's that idea of the day. The antiderivative of an exponential, a to the x, is a to the x over natural log of a. So in this case, it's 1/2 all to the x over natural log of a half. So I'm ready to go. uv is x times that big ugly thing, 1/2 to the x over natural log of a half. Is it plus or minus in Voodoo? Minus. And Voodoo is 1/2 to the x over natural log of a half dx. Ideally, your integral is easier, and it looks pretty complicated, but is it really that complicated? No, because natural log of a half down below is a constant. So if I mentally move that 1 over natural log of a half out front, then it's really just integrating 1/2 to the x. And when I integrate 1/2 to the x in, what do I get? 1/2 to the x over another natural log of a half. So we'd have a pair of natural log of x, natural log of a half in the denominator. That's all true. Do you follow me? Okay. How about the next one? That's got an exponential in it, but it's also got another term. What do you reckon? This is a product. Is this a chain rule kind of derivative case? Looks like a chain rule derivative to me, so what do we do? U sub. So what's u? X squared du is 2x dx. So if I go a substituting, 7 to the x squared becomes just 7 to the u. The x and the dx together could be replaced by du over 2 or 1/2 out front. Okay, the limits, they need to change. When x is 0, u is 0. When x is 1, u is 1. Okay, so 1/2, and again, what's the antiderivative of 7 to the u? 7 to the u over natural log 7 or natural log u? 7. Okay, from 0 to 1, so that's 1 over 2 natural log of 7 out front. And 7 to the 1 minus 7 to the 0, that's just 7, right? Going too fast. It is very common that when people see a 0, they think, oh, that's a wash, that's nothing. Is 0 nothing when you put it in an exponential? No, it's a something. So this is more like 6 in there over 2, maybe 3 over natural log of 7, if you like. You cool? Alrighty. Good volume practice, but I think we're going to have to go on to the back. All right. So we've talked about inverse trig of yucky cases, and I think there was one on the homework yesterday. We talked about something like this where you had to factor out like a 25. You know what I'm talking about, Luigi? We did something like that in the homework, right? Are you with me? Yes. Okay. So that's what these are a review of. Did that go okay, or do you want to review that idea first? Okay, cool. Let's focus on the second idea of the day then, and that is sometimes you get an arcsine or arctangent where you have to complete the square. So remember, arctangent is when you anti-differentiate 1 over 1 plus u squared. That's arctangent of u. And when you anti-differentiate 1 over the square root of 1 minus u squared, that's arcsine of u. Are those starting to get into your memory? Okay, now, this guy, it's not a u sub. That's the first thing that would go through my head is that it's u sub. It's not a u sub. The powers just don't work. There's no x's up top, so that's a no. I think, okay, well, maybe it's arc sine. It's got a root. There's some subtraction action there, so maybe, okay? Let's go there. Maybe we can get a perfect square. We need to say, can we make this some kind of perfect square? Well, let's try. What could I do first? What are you at? I don't like those negatives. Let's start there. I never complete the square with negatives, so I can take a negative out of the x terms. It's still got to stay in the root, because I definitely don't want to pull a square root of -1 out. That's disastrous, right? You bet it is, Mr. Okay, now then, let's see if we can do a little more. In that xe parentheses, let's try and make it a perfect square. What goes there? 1. Now, did I really change the quantity by +1, or is that really a -1 I just changed from? By virtue of the negative out front, that's really a -1. So to balance in the root, I need to add 1. It's a -1, so to balance, I need to add 1. All right, so when I go to write this, isn't that negative the square of x plus 1 squared plus 1? So that is 1 over the square root of 1 minus x plus 1 squared. Is that starting to look arc sine-ish? Yeah, it's arc sine with a u of x plus 1. I don't know if I actually have to use of it. Maybe I could just go straight to the answer. It's the arc sine of x plus 1. Sometimes then you have to complete the square. Try the one off to the side, except you're not shooting for arc sine, you're shooting for arctangent, because there's no root and it's a positive square. So think arctangent. I'm trying to get up to you. Do you get something like 1 over x minus 2 squared plus 3? All right, now that's, you're doing well, but the 3 now is a problem. Okay, we want it to be a 1. You follow? So this is back to those skills of, I want it to be a 1, so I'm going to take out a 1/3, which means this is really 1 over x minus 2 squared over 3 plus 1, you see. All right, now it's feeling like u squared plus 1-ish. I can integrate 1/3 arc tangent of, now the arc tangent of u, now the question is, what's u? X minus 2, is that u or is that u squared? That's u squared, so it's u. X minus 2 over root 3. Plus 1. And I just broke math. I just made a mistake. That sucks. So I was cutting corners here. I tried to cut corners and I failed. So u squared is x minus 2 squared over 3, yeah? And therefore u is x minus 2 over root 3. Everything's going fine, but what did I neglect? Yeah, du. I kind of just blew off the du. So what's du? It's 1 over root 3 dx. So if I actually were to substitute that, isn't that dx root 3 du? I need to slow myself down, basically, is what I'm saying. Okay? Are you tracking with me here that the du matters? Okay, so when I go to substitute, I have the 1/3, it's cool, but that dx is actually root 3 du over u squared plus 1. So the antiderivative is actually root 3 over 3 arctangent of u, which is x minus 2 over root 3. I was way too cavalier with the du and the dx. Okay? Okay, that's all we have time for. Hopefully that'll get you started. So obviously we don't have time for questions on 72, so I'll take 72 and 73 on Monday. Have a good weekend. Yes, it's your lucky day if you're took weasels into your homework. Lazy weasels rejoice. Yay. Oh, see? That's why everybody's going to be doing that stuff. Ay, ay, ay. So what would you quote? Oh, who's that? Really? I like it. Cool.